So today we're going to talk about similar polygons. In subsequent lessons, we're going to focus more on triangles, similar triangles, but we're going to start with polygons. So we want to be able to identify polygons that are similar and to apply the properties of similarity to solve problems with those figures. And as we're doing this, I want you to think about what is the difference between congruent figures and figures that are similar. We have three vocabulary terms. One is what does similar mean? What are similar polygons? And what is the similarity ratio? So when we talk about similar figures, we need some new notation. And this little wave shape means similar to. So when we relate to two things with that figure, it means the first one is similar to the second one. And what does similar mean? Well, similar means that the figures have the same shape, but they're not necessarily the same size. Remember, when we talked about congruent figures, congruent shapes have exactly the same size, exactly the same shape. Similar figures, well, they're the same shape, but they may be smaller. They may be the same size, but they may also be larger than the other figure. And so if we look at the two examples below, the one on the left with the two triangles, triangle one is similar to triangle two. Clearly, they're not the same size. The second one is bigger, but they are the same shape. And so we could say triangle one is similar to triangle two. If I look at the second example on the right, the red and the blue triangle, triangle one and triangle three, clearly they're not the same size, but they're also not the same shape. One is a right triangle, the other one looks like it's isosceles. And so triangle one is not similar to triangle three. And you can see in this little squiggle here, they put a line through it. Now, I would be careful about that because it almost looks like an X, but if you're clear about the notation, then this would mean triangle one is not similar to triangle three. So if we're going to make a claim that two polygons are similar to each other, there are two requirements. The first one is the same for congruent figures as it is for similar figures, and that's that the corresponding angles, the matching angles, have to be congruent. So the corresponding angles are congruent. That's true both for congruent figures and for similar figures. But for the second requirement, similar figures do not have to be the same size. And so the sides of the figure, the corresponding sides, do not have to be congruent. They just have to be proportional. They have to be in the same ratio to each other. And so we'll say corresponding sides, that is bad writing here, corresponding sides are proportional. We can see both those things in these two quadrilaterals. So you can see in the diagrams that we have quadrilateral A, B, C, D, and just like when we're naming congruent figures, similar figures have to be named in a very thoughtful way in that the corresponding angles have to match. So if I start at this right angle and then move to angle B, which has one tick mark, when I start naming the second figure, I have to start at E and then go to F, which has one tick mark. So you have to name them in the same order. So A, B, C, D is similar, and we have the little squiggle, to E, F, G, H. Now there are other ways we could name those, but we just have to match up the corresponding angles when we name them. Because when I see this statement, I can make the assumption that A is corresponding to E, B corresponds to F, C corresponds to G, and D corresponds to H without the picture. And so the two things that are true are all the angles are congruent. So A is congruent to E, B is congruent to F, and so on. So all the corresponding angles are congruent. And the side lengths are in the same proportion. Now, you could name them in any order. I can go from in the sense that I can start at the small figure for the numerator and use the larger figure corresponding side for the denominator, or I could do the reverse. So the ratio I have here is 1/2, but I could also have a ratio of 2 if I went in the reverse order. So AB corresponds to EF. I'm either going to have a ratio of 6 divided by 12, which is what we have for 1/2 here, or if I decided to go the other way, then it would be 12 divided by 6, and I would have 2 over 1. Both are correct. So we're going to talk about the similarity ratio, and that's the ratio that we just discussed about the lengths of the corresponding sides of two similar polygons. So if I talk about the similarity ratio of ABC to DEF, that's going to be different than if I talk about from DEF to ABC. So if I want the similarity ratio from ABC, which is smaller, to go to DEF, then it's going to be a fraction that is smaller than 1 because I'm going from smaller to larger. And so this fraction, if we look at it, I can see that AB corresponds to DE. So AB has a length of 3, and DE has a length of 6. So I have 3 over 6. And so the similarity ratio from ABC to DEF is going to be 1/2. Now, if I talk about going the other way from DEF to ABC, then I could say, well, DE is 6 and AB is 3. So then I'm going to have from DEF to ABC, I'm going to have 6 over 3, which is 2 over 1. Now, in previous classes, you might have talked about scale factors, and this is a little different because the similarity ratio, you can see if I want to get from 3 to 6, I have to multiply by 2. So the similarity ratio is not, the direction is from small to big, but I'm not multiplying by the similarity ratio of 1/2. I'm actually doing the other similarity ratio. I have to double it. And so that's the idea of a scale factor. So this is kind of like the scale factor from the small to the large. The scale factor, what I would multiply by the sides of the larger figure to get to the smaller, would be 1/2. So in this first example, we want to identify the pairs of congruent angles and corresponding sides. So one handy thing is to maybe mark use some color to mark the corresponding angles and corresponding sides. And so we have N is the right angle, so that's going to match Q. And I can see that this angle 63 is P, that's going to match R. And angle M is going to match T. So I can write on my corresponding angles, I can say angle N is congruent to angle Q because they're both right angles. Angle M is congruent to angle T. Now, why would that be true? That would be true because of the third angle theorem, because I have N is the same as angle N is congruent to Q, angle P is congruent to R, so this third angle has to be the same in the triangle. So angle M is congruent to angle T, and angle P is congruent to angle R. So there's my 3 pairs of congruent angles, and now I have to show that the sides are in proportion. So I have to find the matching sides. So let's start with the side that's between N and M. So if I take NM, that's going to correspond. So I went from red to green. That's going to go to QT. So I'm going to have the ratio of NM to QT is going to be 2 over 1. Now, if these are in fact similar polygons, I should get that same ratio for all the other pairs of sides. So let's continue on. So here I have, I did NM, let's do MP. So I'm going green to blue and then green to blue. So we have 2.2 divided by 1.1. So we're going to have MP to TR, and that's 2.2 to 1.1, and that is also 2 over 1 if I reduce that. You can reduce it as a fraction. You can also outright divide it. Sometimes when you have decimals, it's easier to just divide it and see that the numerical value is the same. So the last side we're going to talk about is PR, or PN rather. So side PN, that's going blue to red. And then we're going to go blue to red in the smaller triangle, which is RQ. And so PN has a value of 1. RQ has a value of 0.5. And 1 divided by 0.5 is also 2. So we have 2 over 1. And we can see that now we've shown that these two triangles meet all the requirements for similarity. So we're going to write a similarity statement. I'm going to say triangle NMP is similar to triangle QTR. And then we've shown everything that needs to be true, and we've written our final answer as a similarity statement. So this is just a brief reminder that order matters when you're doing similarity statements, just like order matters when you talk about congruence. Because when you're done matching up, you're writing your statement. For example, if I said triangle ABC is similar to triangle FGQ, that means that this A has to be corresponding to F, and B has to correspond to G, and C has to correspond to Q. Now there are other ways we could name it. We certainly could. I could name the triangle BCA, but then my similarity statement would have to start with instead of this one started with the middle one, so this would have to start with GQF. So there's different ways to name it, but the corresponding angles have to match. So here we have a pair of rectangles, and we want to decide, are these rectangles in fact similar? Well, one easy thing about rectangles is we know that all the angles are 90 degrees. So I know that angle B and angle F, they would correspond. Angle C and angle G would correspond. Angle D and angle H, they would correspond. And angle A and E, they would correspond. And all those corresponding angles are right angles, so therefore they're congruent. So I can just make this the generic statement. I could say all the corresponding angles are congruent because they are right angles. So that takes care of the congruent angles. Now I do have to show that the sides are in proportion. But again, with a rectangle, we luck out because we know that the width is going to be the same for all of these lengths, and the length is going to be the same for all of these lengths as well. So we just have to show it for one length and one width. And so I'm gonna check out. I'm going to start from the larger to the smaller. So we're going to show BC to FG. And BC to FG would be 9 over 6. And I can divide both of those by 3, so that would be 3 over 2. So when I look at BA over FE, it should also be a ratio of 3 over 2. So I have 6 over 4. I can divide both of those by 2. 2 into 6 is 3 times. 2 into 4 is 2 times. And so there we've shown that the sides are in proportion. So yes, these are similar figures. So let's write a similarity statement. So I'm going to write rectangle BCDA is similar to rectangle FGHE. And again, I didn't show all four sides because we know on a rectangle that 2 of the sides have the same length, and same thing for the 2 pairs of the sides are the same length. So now we're going to look at an example with 2 triangles. And we can see these triangles do not look like they're the same shape. But just because they don't look the same doesn't mean they are not the same. So we have to check this out. So one of the things I notice is the first triangle here is an isosceles triangle. It's got two sides that are 10 and 10. And so if that's true, then these two angles at the bottom here have to be congruent. They have to also be the same. And so I have a triangle has 180 degrees. So if I subtract 36 out of that, so 180 minus 30, that's 150, and I'm going to take 6 more. So that's 144. And so these two angles that I would have left are going to be half of that 144. So if I take half of 100, that's 50, half of 40 is 20, half of 4 is 2, so that's 72 degrees for each of these. Now at this point, I can stop, because what I've shown is, in fact, that the angles are not all congruent. So I have this 36 degree angle, and I have a 72 degree angle and a 72 degree angle. Nowhere is there a 62 degree angle. So I don't have to do any more work. I can just say they are not similar. And I would actually prefer that than, using that statement with the line through it. Write it out. And that results in a value of 17.5. So that 17.5 is the length of the model car. It would be 17.5 centimeters. Okay, so we're going to move through a couple of check it out examples. And what I'd like you to do is to try the problem, pause the video. So put it on pause, and then I will have the answers in a minute. Okay, so hopefully you tried the problem, and I'm going to show you how I would do it. So the first thing we're going to do is we're going to match up the corresponding angles. So the right angle matches the right angle, so B matches G. I can see that the 59 degrees at C is going to match H, and then the third angle, which has to be congruent by the third angle theorem, A and J are going to match. So we're going to write that out. So we're going to say angle, we'll start with A. Angle A is congruent to angle J, and that would be by the third angle theorem. Angle B has to be congruent to angle G because they're both right angles. And angle C has to be congruent to angle H because they both have the same measure, and that's the definition of a congruent angle. So now we're going to identify the corresponding sides, and so I can see between the green and the red angle, AB, so AB is going to correspond to JG. So the ratio of AB to JG is going to be 10 over 5. And so it looks like a ratio of 2 to 1 from the big one to the smaller one. The big one appears to be twice as big. So let's see what we get for the other one. So we did AB, so now let's do BC. So BC over GH. BC is 6, GH is 3. So that's 2 over 1. And then we just have to check one last value. So we're going to go blue-green. We're going to do CA in the large triangle, and that should match HJ in the smaller triangle. And so that's 11.6 divided by 5.8. And you can see that if I double 5.8, I get 11.6. So that's also 2 over 1. And so there we've shown it. The corresponding angles are congruent. The corresponding sides are proportional. And then we could make our congruent statement. So we can say triangle, and for the first triangle, it doesn't matter how we name it, but let's just do ABC because it's in order. So triangle ABC is similar to triangle JAB. G, H. So the order that we went in the order of green, red, blue. So I had to do green, red, blue for the second part. So here's the next problem, and it says determine if triangle JLM is similar to triangle NPS, and if it is, then we're going to write the similarity statement. But if not, we don't have to do that. So pause the video, and then once you have tried it, you can check out my work. So let's match up the corresponding angles to start with. So I can see that this right angle here is going to match this right angle. We have this angle with one tick mark L, that's going to match angle P because that has one tick mark. And then by the third angle theorem again, J is going to correspond to S. So we do know just by going through that exercise that angle M is congruent to angle N because they are right angles and all right angles are congruent. We know angle L is congruent to angle P because they each have a single mark on each angle indicating that they are the same measure. And then by the third angle theorem, angle J is congruent to angle S. So we know all the angles are congruent. Now we just have to show the sides are in proportion. So let's start by identifying a side we're going to match up. So if we go from the green to the blue, so this would be green to blue in the smaller triangle. Green to blue in the large is JL, so we're going to look at JL, and JL is 75, so that would be in the numerator. And we're going to match that with SP, and SP in the smaller triangle going from green to blue is 30. So we want to reduce this, and so I know that 5 goes into both of these. 5 goes into 36 times. 5 goes into 75 15 times. It could go further than that, though. That's not all the way down, so I missed a factor. So there's 3 goes into 6 twice. 3 goes into 15 5 times. So this is 5 over 2. So the ratio is 2.5. So let's see if the other sides give us the same value. So we did JL, let's do LM. So LM, blue to red, we go PN. And LM is 60, PN is 24. And so what's the common factor? 12 goes into 65 times. 12 goes into 24 2. So that's in the right proportion. And then we just have the last side to do. So we did LM. Now let's do MJ, red to green. And so we're doing NS, which is red to green in the small one, NS. And so we have 45 over 18. And 9 goes into both of those. 9 goes into 45 5 times, 9 goes into 18 twice. And we can see we've shown everything we needed to show because we now know that the corresponding angles are congruent and all of the pairs of corresponding sides are in proportion. So we can write the similarity statement. So again, the similarity statement, we just have to be in the correct order. It doesn't matter which order we start naming it. So I'm going to say triangle, and let's do green, blue, red. So I'm going to say triangle JLM, JLM, and I'm going to use the single squiggle for similar. And so I did green, blue, red. I have to go green, blue, red from the small one. So I'm going to do SNP, similar to triangle SNP. So in this problem, they give you a box car and a model. So a box car like a train car. So the model of the box car is 1.25 inches wide, and they want you to find the length of the model to the nearest inch. So we're assuming that these two figures are similar because if they are similar, we can set up a proportion to do this. They probably should have said they were similar rectangles. And so here I have, we're going to match up the corresponding length and width. Again, if it's a rectangle, I don't have to, I only have to do 2 lengths. And so here we have the the length of its of the figure, and then we have the width to match up. And so we're going to say 36.25 feet divided by x. And again, even though one figure is in feet and the other is in inches, it's not going to matter for this application. And that's going to be equal to, so I have the boxcar on top, so I'm going to put the width of the boxcar on top, 9 to 1.25. And so we'll do our cross multiply. And so we'll have 9x is going to be 36.25 times 1.25. And then when we divide by 9, we'll have x is going to be 36.25 times 1 1/4 divided by 9. So when we do that, when we divide that out, we get 5.03472. So it's 5.03472. Now, of course, most of that we're not interested at all. We have 2 decimal places in this measurements here, and so maybe we'll keep 2 decimals. But if you look here, the width of the boxcar is only given to a whole number. And actually I didn't read carefully. It says to the nearest inch. So we can truncate all that last bit off, and so we're going to say x is 5. Okay, so this is going to be 5 inches, and we're done.